Hello, everyone. Thank you for joining us for the 7th session of Ocean Acidification Week 2020, a virtual multi-day forum to highlight ocean acidification research and initiatives. OA Week is presented by GOA-ON, the Global Ocean Acidification Observing Network, by NOAA, the National Oceanic and Atmospheric Administration, by the IAEA OAICC, the International Atomic Energy Agency Ocean Acidification International Coordination Center, and by the IOC-UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. This session will feature talks from around the countries that surround the Northeast Atlantic Ocean. We are glad to have about 156 people pre-register for today's session. Today, there are currently about 54 people on the call, and we hope the rest join very shortly. My name is Michael Aquafreda, and I work with the GOA-ON Secretariat. I'm also a Knaus Fellow working with the NOAA Ocean Acidification Program. I will be moderating today's session. During today's presentation, all participants are in listen-only mode. You are welcome to type any questions you have into the questions box, which can be found at the bottom of the control panel on the right-hand side of your screen. You can also pose questions and share your insights on Twitter using the hashtag OAWeek2020. We do ask that you specify the speaker you're directing your question to. We'll be monitoring incoming questions and will pose them to our speakers during the questions and answers section, which will begin immediately after the last presentation. Today's webinar is being recorded and will be available through the GOA-ON YouTube channel shortly after OA Week ends. Before we start, I would like to briefly share some information about GOA-ON. GOA-ON is a collaborative international network designed to address 3 high-level goals. First, improve our understanding of global ocean acidification conditions. Second, improve our understanding of ecosystem response to OA. Third, acquire and exchange data and knowledge necessary to optimize modeling for OA and its impacts. GOA-ON is an active organization that offers numerous resources to its members. GOA-ON informs policy at the international level. GOA-ON is involved with the Commonwealth Blue Charter and the UN Decade of Ocean Science for Sustainable Development 2021 to 2030. More specifically, GOA-ON also assisted with the UN Sustainable Development Goal 14, by helping to develop the methodology for the SDG indicator 14.3.1 by providing guidance on how to measure ocean acidity and how to report the collected information. GOA-ON also offers a scientific mentorship program through peer-to-peer. The peer-to-peer program matches senior researchers with early career scientists to facilitate an exchange of expertise and to provide a platform for international collaborations. Scholarships and hands-on trainings are available through peer-to-peer. GOA-ON also hosts a data portal, which provides access and visualizations to OA data and data synthesis products, which are being collected around the world. Data are present from a wide range of sources, including moorings, research cruises, and fixed time series stations. Finally, and most recently, GOA-ON's newest resource is a webinar series. In fact, Ocean Acidification Week 2020 is the kickoff to this new GOA-ON webinar series. Future webinars will take place every 4 to 6 weeks. We welcome your inputs on what topics you would like to hear about in the future. If you have any ideas for future GOA-ON webinars, please type them into the questions box at any time during today's session. GOA-ON has 8 regional hubs, and we'll be hearing from most of those hubs throughout OA Week. Overall, GOA-ON has over 750 members from over 100 countries. If you're interested in ocean acidification or are an ocean acidification researcher, we recommend that you join GOA-ON by going to the goon.org website. One reason why GOA-ON decided to host Ocean Acidification Week is because initially, the 5th International Symposium on the Ocean in a High CO2 World was scheduled to take place this week in Lima, Peru. Yet, like many other events scheduled for this year, the symposium had to be postponed until 2021. The symposium would have brought together researchers, decision makers, and stakeholders to share cutting-edge ocean acidification science. We're looking forward to the symposium and hope everyone listening today will visit the symposium's website and learn more. We'll see you in Lima in 2021. At this time, it's my honor to introduce our speakers for today from the Northeast Atlantic Hub. The first speaker is Filippa Fransner from Norway. Next, we'll be hearing from Rachel Cave from Ireland. Then we'll be hearing from Vassilis Kittidis from the UK. Next, we'll be hearing from Elisa Guallart from Spain. And finally, we'll be hearing from Maribel Garcia Ibanez from the UK. However, before we hear from these speakers, I would like to share a little bit more information about the Northeast Atlantic Hub. And to do this, I would like to introduce the co-chair of the Northeast Atlantic Hub, Helen Findley. Helen, at this time, please unmute yourself.
Hi, good afternoon, good morning to everyone, wherever you are in the world. And thank you for joining us today for this session on the last day of OA week. It's been a fab week, and hopefully we can live up to that by sharing with you some of our research around the Northeast Atlantic. So our hub was formed in November 2018, so a relatively new hub. We're coordinated by the Plymouth Marine Laboratory, by myself, Helen Findley, and coordinated by Steve Widdicombe. We've had some financial support from the UK government through DEFRA, which has enabled us to host a workshop in March and some executive group meetings over the last couple of years. We have currently up to over 80 members from around 13 countries around the Northeast Atlantic region, and we have a register of over 78 monitoring activities or assets. So these include things like fixed point moorings, ship-going activities, and those range from relatively new ones that have just started up in the last couple of years, but we also have long-term time series spanning back to around 1993. Our aims are to really share knowledge in our region. It's a very diverse region. There's lots of specific types of habitats and biological and chemical properties within the region. So we'd like to be able to share knowledge and facilitate data exchange within our region, as well as bringing the community together following the general GOA-ON aims. I'll pass on to the speakers. This first session is all about the goal 1, really, for the GOA-ON aims, which is to improve our understanding of global ocean acidification conditions. So it's very much to do with the chemistry, understanding vulnerable regions, mechanisms, and how we can improve our monitoring activities. Thank you.
Thank you so much for that overview of the Northeast Atlantic Hub, Helen. At this time, I will make our first presenter the presenter. Filippa, you are now the presenter. Please share your screen, and you can unmute yourself.
Can you hear me and see my screen?
We can hear you. Go ahead and make your presentation full screen. That looks excellent, Filippa. Take it away.
Okay, thank you for giving me the opportunity to present here. And this is some work on Nordic seas acidification. It was started by Are Olsen and then carried on by Fredrike Fröb, and now I'm finalizing it. And there's a lot of input from many researchers and many institutes. And we hope to, or we will submit this next week is the idea. Yes, so the objectives of this work is to provide an overview and a deeper understanding of the acidification in the Nordic seas. And we've been looking to several time periods, past, present, and future. And we've been looking into horizontal and vertical variations in the acidification signal, and also underlying drivers, including dissolved inorganic carbon, changes in alkalinity, temperature, and salinity. And finally, we have been looking into impacts on the Aragonite saturation state, and cold water corals. So for this work, we've been using basically all observational data that we could find from cruises and from time series stations, and also from the GLODAP gridded climatology. And we've been focusing on 6 regions that you see here in the map: the Norwegian Basin, the Lofoten Basin, Barents Sea opening, the Fram Strait, the Greenland Sea, and the Iceland Sea. Then for past and future acidification, we've been using output from the Norwegian Earth System model. That is a fully coupled model, including an atmospheric module, a land module, ocean physics, ocean biogeochemistry, and sea ice. More specifically, we've been using CIMIP5 simulations. That includes a historical run from 1850 to 2005 that follows its force with historical atmospheric CO2 concentration that you see here. And then we've been looking into 3 future scenarios following different CO2 concentrations of the atmosphere. So the least worst scenario is the RCP 2.6. Then we've been looking into RCP 4.5 and RCP 8.5, where we have concentrations going up to 1,200 ppm by the end of the century. Yeah, and here you see an overview of the pH of evolution, the average pH evolution in the Nordic seas that we get from all these data sources. So here we have the past evolution from 1850 to 1980 that is based on the NORISM simulations. Then we have the present evolution from 1980 to 2019, where we see both the simulations from NORISM and the observational data, which is the black dots with the error bars, and the 3 different future scenarios: RCP 2.6, 4.5, and 8.5. And in this presentation, I will mostly focus on the present times, and then just give a short summary of the past and future. So we go into the present trends in the 6 different regions. Oops. Yeah, we're back on the right slide. So here we see the trends in the Norwegian Basin, the Lofoten Basin, Barents Sea opening, Fram Strait, Greenland Sea, and Iceland Sea. And they lie around -2 to -3 millipH per year, with the Lofoten Basin and Barents Sea opening being exceptions. Then if we look into the drivers behind these pH changes, we see the contribution here of temperature, salinity, DIC, and alkalinity to the total change. And the different bars show the change for each region, but I'm not going into the regional differences. But what we see in general is that there's an increase in DIC that is the main driver of this pH decrease. It's slightly opposed by an increase in alkalinity and a cooling. And what's interesting is also that we see that the pH decrease is stronger than we expect from the increase in atmospheric PCO2. And we find that this is related to a faster increase in the seawater PCO2. So compared to the atmosphere. So the PCO2 undersaturation of the Nordic seas is decreasing. Yeah, and then if we go to deeper waters, so the last slide was on surface waters. Now we go into deeper layers. Here is 200 to 500 meters. The pattern looks the same, but the signal gets weaker. The only exception is that in deeper waters, we have a warming that is reinforcing the acidification. And then the pattern looks similar if we go deeper, and we see a significant acidification all the way down to 1,000 to 2,000 meters of depth. In the Norwegian basin, the Greenland Sea and the Iceland Sea. Below this, there is no significant change. Then if we look at the Aragonite saturation states, we see that there is also a significant decrease down to 1,000 to 2,000 meters. And in these waters, we see also that they approach undersaturation, so it's getting very close to 1. Yes, so that was for the present times. So if we look compare that to past and future, we see that from 1850 to 1880, we have a drop of 0.05 pH units. So that's the last 40 years, we had a change that is twice as much as that. And in the future, we will see an additional drop of 0.1 to 0.5 units. For all time periods, we see that DAC is the main driver. In present times and also in future scenarios, we see that this is slightly opposed by an increase in alkalinity and reinforced by a warming. For all time periods, we saw that spatial variations in acidification rates were dependent on regional variations in the change of the PCO2 difference between the atmosphere and the seawater. And that this is more important than the regional variations in buffer capacity. And this is something that we need to dig more into to better understand the pH change in the Nordic seas. And then for the impact on deep water or cold water corals, we see that until present, so this is the black line here. So here we have depth and the number of observed reefs. We see that the saturation horizon lies well below the observed coral reefs, which is this histogram here showing the number of reefs per depth. Then in future scenarios, we see that also for RCP 2.6 and 4.5, the saturation horizon lies below most of the corals, but in RCP 8.5, all of the corals will be covered in undersaturated waters. Yeah, that was all. Thank you.
Thank you so much for that presentation, Filippa. At this time, I'd like to introduce Rachel Cave. Rachel, I've now made you the presenter.
Okay, I just need to show the correct screen here again. Let's just see screen 2. Okay,
Rachel,
so I hope you can see.
Yeah, we could hear you and we could see your screen. It looks great. You could take it away.
Excellent. Okay, so I'm going to talk to you today about the impact of water masses on ocean acidification conditions in canyons along the Irish shelf edge. So I'm Rachel Kay, but I'd like to highlight the three early stage researchers who have been involved in some of this work. Aideen McAleer, who's my research assistant on the VOCAB project, which is our current ocean acidification project. Yanina Busher, who's recently joined us from Guallart as a postdoc, and a PhD student, Owen Daly, who works in the physical oceanography group. So the others are all late stage researchers. So if we look here, we're looking, sorry, I should say that Aideen and Hanina are currently somewhere east of Iceland taking samples. So I think we may be interested in talking to Filippa later because they've been doing some work up in her area in the last couple of weeks. So the Irish shelf forms the eastern boundary of the Rockall Trough, and it's very heavily incised with canyons. Okay, you don't get that on the western side because the canyons were formed during low stands of sea level when the rivers came right out to the shelf edge, and then subsequently by sedimentary action as sea level rose. But in both cases, you have this immensely biodiverse fauna and a huge amount of cold water corals living both in the canyons and also along the western side of the trough. But we wanted to have a look at the canyons. So our project is funded by the Marine Institute and we carried out at the Ryan Institute in NUI Galway. So for the last 10 years or so, we've been doing transects across the Rockall Trough, looking at ocean acidification parameters. And we've published some of that data already with McGrath et al. In 2012. But in 2018, we had the opportunity to take part in two surveys, ROV surveys run by our biological colleagues, one in University College Cork, Aaron Lim, and an NUIG colleague, Louise Alcock. And they were going to look sort of north and south of our normal line. But we took the opportunity to go out there and take some water samples. And we wanted to compare the ocean acidification conditions north and south, because the Rockall Trough is an area where a lot of water masses from the North Atlantic meet and mix. Okay. So we looked at 6 individual canyons in the northern part, and then in the southern part, it's one sort of a canyon complex, which has several arms to it. Okay. And we wanted to look at this to see if there were significant differences north and south, and that this might give us some idea of the natural variability of the water chemistry, and also of the tolerance of the species living there to variations. You can kind of think of the Rockall Trough as a bit like a large estuary that operates on a very slow scale. So rather than the tides coming in and out, you have changes on an annual basis in the volumes of water and the amount of each water mass that gets into the trough every year. So the maximum depth we were down to in the canyons was about 2,400 meters. So the trough itself goes down to about 3,500 meters, but just along the flank, it doesn't get that deep. So first of all, I'd like to show you a temperature salinity diagram. This is from the northern Kittidis, the northern canyons that we looked at. And pretty much the top 1,000 meters of your water in the Rockall Trough is eastern North Atlantic water. Okay, and we have what we call here the Harvey line, which is what we use to show us if your water mass falls within the Harvey line, then it's pretty much eastern North Atlantic water. But we do have a couple of other water masses which can come in. This little bump here in the middle we tentatively assign that to subarctic intermediate water. And then down at the bottom here, we have the beginnings of Labrador seawater in the deeper water. You can, in the northern part of the trough, also find Wyville-Thomson overflow water. Okay, but you don't tend to find it in the south. And we don't tend to find Mediterranean water in the northern part of the trough. So this is the cast then from the southern part. So again, temperature salinity, and you can see here we have the Mediterranean water over on the right. So it's well off the Harvey line. So we're now, it's clear the eastern North Atlantic water is being very strongly mixed with the Mediterranean water coming from the south. So top 1,000 meters eastern North Atlantic water, but within that then we have these two other water masses appearing in the north, subarctic intermediate water, and in the south, Mediterranean water. And they both have effect on the chemistry. And just in case you're not familiar with the Rockall Trough, this relief map here shows you that at the northern side of that, it only gets down to about 1,500 meters maximum. So there's a very limited amount of water from the North Atlantic can actually get in. It's essentially what comes over the Wyville-Thomson ridge from the Norwegian seas. But down in the southern end, you've got water coming eastward across the Atlantic that comes in up one side of the trough, and you also then have water coming up from the south, and they tend to mix and circulate in the northern part of the trough. So if we have a look now at some profiles, the purple data are from the northern stations, and the orange data are from the southern ones. And you can see there's quite a big temperature difference. So there's about 2 degrees down to 1,200 meters difference in the temperature. If you look at the salinity, again, the purple one's in the north, the 2 arrows are pointing to where we think on the left here we have subarctic intermediate water. So this is a slightly fresher bump coming in there. And then in the south, we've got the clear indication of the Mediterranean water. But the net effect of this cold fresh water and warm salty water is that the density tends to converge. Okay, so you can get an interleaving of water masses that are at the same density, so it can make it quite difficult sometimes to discern very clearly which water mass you've got. Okay, so I'll put in this sort of block which runs across from about 500 to around 1,250 meters or so, all the way across with all the slides that we're doing. So I'm keeping the salinity here, and now we're going to look in the center at the oxygen. Again, the northern ones in the purple here, you've got your oxygen minimum between about 500 and 1,200, which is the normal thing we expect as we've got remineralization of organic matter, but it's much stronger in the southern end because the Mediterranean water is already low in oxygen. So that's the first thing we can say, that organisms living at these depths, okay, are experiencing much lower oxygen conditions in the southern canyons than they are in the northern ones. And I just put in the nitrate here just to show you what the nutrients are behaving as we'd expect, very low in surface waters in summer, and then you've got a maximum in your nutrients at around the same place as your oxygen minimum is. Okay. So then we have a look at the carbonate chemistry, which is the bit we're most interested in. Again, purple is your northern ones, and orange circles are your southern ones. And you can see then that you've got an increase in total alkalinity. So this is because your Mediterranean water is pretty salty. Okay, and here again, sort of around about the 800 to 1,000 meter mark. Okay, you've also got an increase in DIC in the Mediterranean. Okay, and it's the DIC, the dissolved inorganic carbon. This is Filippa mentioned earlier. This is what's driving the pH. Okay, so your southern canyons have a slightly lower pH in general than your northern canyons do, at least this year. And again, this will depend on the strength of the Mediterranean outflow water in any given year as to how strong that influence is. Yeah, and I guess one of the things to remember with pH, a bit like temperature, pH is one of the things that mediates metabolic function. So it mediates the chemistry that's going on and related to uptake of nutrients and metals and so on. So any change in pH will have some impact on how the organisms are functioning. So oops, going too fast. So again, we've kept the salinity so you can see where we're talking about, and then we look at the other really important aspect of carbonate chemistry, which is the aragonite saturation. Okay, so if we look here, aragonite saturation is pretty high in surface waters, and then it starts to decline. And we've got then a slightly lower aragonite saturation around about the 1,000 to 1,200 meter mark in the northern canyons than we do compared to the southern ones. And then once we get down to around the 2,000 meters, we're getting very close to an aragonite saturation of 1. And as I'm sure you're all aware, is once you get below 1, your organisms are unable to precipitate aragonite, and you're not going to have corals and so on living there. Okay, and again, just the pH, just for comparison. Okay, so then if we have a look sort of in the slightly bigger, so just compare what we're seeing in the canyons with what we've seen in recent transects. So this is the 2017 transect across the Rockall Trough, which kind of falls between our northern and our southern canyons here. And you can see a very similar trend. This was a winter one, so it's about 18 months before the 2018. You can see you've got slightly lower saturation in surface waters, and that's because it's winter time, and so you're able to, colder waters, you're picking up more DIC and you don't have much biological activity. We unfortunately have a gap in the 2017 data right around the 1,000 meter mark, so it will be interesting to see if we see this bump or not. But again, you can see that once you're getting around to 2,000 meters, again, as Filippa pointed out, you're getting very close to aragonite saturation, and in the Rockall Trough, once you're below 2,000, you're well undersaturated. We do have 2019 data, but we haven't analyzed all the samples yet, so we'll hopefully be able to fill in this gap here. So this, I just put in the lines here just to sort of show the sort of the 1.25 saturation, so you can kind of see just how far up the water column organisms are starting to be at risk. Essentially, the lower the saturation, the more effort the organism has to put in to precipitate its hard parts. So it's expending more energy. So you can see that right up to about 1,000 meters here, they're kind of in the danger zone. Okay, and again, as Filippa said, so we're expecting the Aragonite saturation horizon to keep rising. Okay, it's around about 2,000 now, and it's expected to keep shallowing. Okay. So this is just a quick comparison with the pH, and again from the 2017 transect as well, so you can see what the deeper water looks like. Okay, so again, you're down into getting into low pHs here. So I guess the key messages then from this are that the variability of the water masses in the rockall trough is driving the OA parameters at different depths. Okay, we already know that they change from year to year. The amount of Mediterranean water, or whether or not we see the Weigel-Thomson water, changes from year to year. But as the North Atlantic circulation changes, we're liable to see even more significant effects on both temperature and ocean acidification parameters. The one good thing we know about is that since there are differences north and south, and always have been, I guess, that the organisms are likely to be relatively tolerant to the variation, so they'll probably withstand it at least for some decades to come. And then again, as Filippa mentioned, the saturation horizon, it's approaching 2,000 meters in rockall and likely to get shallower. So this is sort of fairly preliminary data, but we're working on the paper at the moment, so we hope to get some more detail out soon. So thank you very much for listening.
Thank you, Rachel, for that wonderful presentation. At this time, I'd like to introduce our next speaker, Vass Kittidis. Vass, I've gone ahead and made you the presenter.
Yep. Okay.
And before we begin, I would just like to remind the audience members that if you have questions at any time, please post them in the questions box. Vass, you could take it away.
Okay, hello. My name is Vass Kittidis, and I'm going to talk to you about some ocean acidification monitoring activities that we at the Plymouth Marine Laboratory are undertaking. Namely the Western Channel at the Western Channel Observatory, and also in the Atlantic Ocean as part of the Atlantic Meridional Transect program. And these contribute to the Global Ocean Acidification Network Northeast Atlantic Hub, which we are part of and coordinate, as Helen Findley said earlier. So the plot on the left-hand side shows you the AMT transects, which is an annual trip from the UK down to South America. And this is, sometimes it happens twice a year. In certain years, it has happened twice a year. But usually it's just once a year. And this is an older plot. You see the cruises go up to 2013, but they happen every year, basically. The Western Channel Observatory is situated in the southwest of England. And what we have here is it's made up of three parts. So there is an in situ observatory, which has atmospheric, pelagic, and benthic components. And we measure a number of different things, including carbonate, the carbonate system. And then there is a remote sensing observatory. So we do a lot of satellite work. And finally, a virtual observatory, which is the modeling. And these three parts, so the in situ, the remote sensing, and the virtual observatory, work very closely together. Now, each one of these has advantages and disadvantages. The Atlantic Meridional Transect gives us great coverage in space, but limited coverage in time. While as the Western Channel Observatory gives us excellent coverage in time, We go there weekly, but it's limited in its spatial extent. And what I would like to say just briefly is that both of these observatories have contributed to a sort of carbon budget for the Northwest European shelf. Incidentally, some data that Filippa showed and also Rachel earlier have also contributed to this. And I've just put there's a reference at the bottom to the article. Okay, so the Western Channel Observatory. So what we have, excuse me. So the Western Channel Observatory, what we have here is carbonate system measurements since 2007, namely alkalinity, dissolved inorganic carbon, PCO2, and pH. We have a mooring, and also we have weekly visits. Sometimes it's every 2 weeks, weather permitting, where we collect samples and quantify the carbonate system parameters in the lab afterwards. And we have a series of stations. Most of our work focuses on the L4 and E1 stations. And you can see these on the map on the left-hand side. And initially, our work focused on describing the carbonate system and the seasonality at these two stations. So you see pH at the L4 station in the middle and at the E1 station on the right-hand side. And what we have is we have a nice seasonal cycle in both cases. However, at the L4 station, the pH is lower in every month, in fact. It is lower than at E1, and it is much more variable. And this has something to do with the proximity to the coast and the influence of rivers. We have a great number of rivers that come into the English Channel from Devon and Cornwall in southwest England. And Helen Findley is currently working on the time series. It makes it, the influence of the rivers makes it more difficult to discern any trends in pH. But Helen Findley is working on the time series and will be submitting a paper later on in the year, which we will publicize through the GOA-ON hub. Okay, the Atlantic Meridional Transect. So my slides keep jumping. So the AMT, here we have carbonate system measurements since 1995. We now have the full carbonate system. So we have alkalinity, inorganic carbon, PCO2, and spectrophotometric pH. And we published a paper in 2017, which showed a decrease in pH of about 1.3 millipH units per year, and also an increase in temperature of 10 millidegrees per year. And this is right across the Atlantic. And what you can see here is on the plot on the left-hand side, the pH against latitude. The colder colors are the older cruises starting in 1995, going up to the warmer colors, in this case AMT 23, that was in 2013. And we're working on updating this to the more recent, including the more recent cruises. Now you will notice on the plot on the right-hand side that the cruise tracks are not always the same. So we spent quite a lot of effort and time in this paper showing that the differences in cruise track do not affect the results in the majority of cases. So we're reasonably confident that the differences in cruise track do not skew or bias our results in some way. Okay, now what I wanted to say here is that both of these platforms, I have to apologize, both of these platforms, we don't just see as monitoring sites, but also as platforms for carrying out process studies. And what I wanted to show you here was a couple of examples. So we've done a lot of work on the impact of ocean acidification on nitrification. Nitrification is a key part of the nitrogen cycle. It's part of the recycling of nutrients, if you like. And what we find is that when we change the pH of sediments, so it happens in superficial sediments, when we change the pH in the overlying water, the nitrification in the superficial sediments carries on as normal. However, the nitrification in the burrow walls of various animals ceases. And that is because these animals basically die. So in this little cartoon here, I've got a little shrimp. The animals die at low pH, and they stop ventilating their burrows. And this is important because they stop drawing oxygen into the burrows, so the nitrification becomes oxygen limited. And under normal conditions, the nitrification in the burrow walls is an order of magnitude higher than it is in superficial sediments. Another example is from the Atlantic Meridional Transect, and here this is from a collaboration that we have with a group in the Netherlands at Naturalis, led by Katja Pijnenberg. And they're specifically interested in the biogeography and evolution of theropods in relation to pH and the carbonate system parameters. Theropods are calcifying planktonic organisms. And they have done some micro CT scanning of shell theropods and ocean acidification experiments as well more recently. And we work together where we sort of work on the carbonate system, and they do some of the experimentation, etc. I haven't got any results to show you because this is work in progress. But we're very much open to collaboration. That's what I would like to finish on. Both for the AMT and at the Western Channel Observatory. We're very happy to collaborate with people, so please get in touch. I've put a couple of contacts there at the bottom, Tim Smythe and Andy Rees, and let us know. Okay, thank you very much.
Thank you so much for that presentation, Vass. I'd like to introduce our next speaker, Elisa Guallart. Elisa, if you're on, you could go ahead and unmute yourself.
Do you hear me?
Yes, we could hear you loud and clear.
Okay, nice.
Are you able to see your presentation?
Okay, yes.
Okay, I'm going to make it full screen.
Mm-hmm.
And Elisa, just let me know when you want me to switch slides by saying next. And then you can take it away.
Okay, thank you. So this presentation focuses on preliminary results relative to the implementation of the method for determining spectrophotometrically carbonate ion in seawater. There is several people involved from different institutions, either in terms of collection of the data or processing and interpretation of the results. So next. And next again, yes. So in face of the current changes scenario, we need to improve our ability to obtain more data records that are of climate-related quality. In this regard, my host institution, the Instituto Español de Oceanografía, is responsible for the monitoring of the Spanish coastal areas and coordinates several surveys that constitute the EOO observing system. In the figure, you can see the different stations from these monitoring sections, and in the table below, a summary of the different programs. I collaborate in the Inorganic Chemical Oceanographic Laboratory, and our lab coordinates the biogeochemical sampling and the related analysis in the time series of this observing system that are located in the Northeast Atlantic. You can see them into the red boxes. They consist mainly of a monthly coastal time series in A Coruña, and we have also collaborated in the Cantabrian Sea, and our lab also visits each year a deep hydrographic section called Radcor in front of Finisterre. We mainly measure pH, alkalinity, dissolving organic carbon, carbonate ion, oxygen, nutrients, and salinity. Next. Sorry. So the method for obtaining spectrophotometric measurements of carbonate ion was first described by Bergen and Yao in 2008, and it mainly relies in the speciation of lead in seawater. In practice, it consists in adding an amount of lead solution into a sample and obtaining a ratio of absorbances. The previous one, you passed 2 slides. No, the previous one. Two before, no. Previous. Yes, sorry, here. So when you obtain this, no, the next one.
Seems to be a little bit of a lag.
Yeah, this one.
We apologize for that.
Yes. Okay, sorry. Well, okay, I will wait. So yes, when you obtain this ratio of absorbances, this is used in equation 3 for obtaining determinations of the carbonate ion concentration. This equation has the same formula, the one that is used for measuring for determining spectrophotometric pH in seawater. And this method has been revised several times. You can see the list of citations into the box. And this has been done with the aim of improving the quantification of the thermodynamic and optical terms included in equation 3. In the table next to on the right, you can see all the several terms that have been proposed to be used for being used in this equation. Next. And this table summarizes the main characteristics of the evolution of this methodology affecting these 5 approaches. Okay, the first one, the first protocol was proposed by Bergen and Yao in 2008, and then successive actualizations and revisions were done by Isley et al. In 2013, by Patsavas et al. In 2015, and by Sharp et al. In 2017, and by Sharp and Byrne in 2019. And the main upgrades consist in a change in the lead region that you add into the samples, which also affects the final concentration into the cuvette for performing the absorbance measurement. And then successive actualizations propose a perturbation correction by Patsavas et al. Due to the addition of region, and also later Sharp and collaborators, the 2 approaches proposed by Sharp, suggest that there is a need to assess the potential wavelength calibration inaccuracies of the spectrophotometer that is used for doing these absorbance measurements. So they propose a correction for adjusting the measured absorbance ratio values to convert them into offset corrected values. And finally, the last approach by Sharp and Byrne permit obtaining these measurements at ambient temperature, while all the previous approaches require temperature control at 25 degrees. Next. Yes, this slide is only contains an explanatory comment for any possible consultation. regarding the particular details of the table that affect the parametrizations of the correction equations. Next. So in this context, our main aim, since we have been performing these measurements in several cruises during several years, we have observed some inconsistencies in our time series. And in this context, the main aims of this study are assessing the evolution of the method by means of evaluating internal consistency of a combined data set that covers a broad range of oceanographic conditions, and also to remark methodological difficulties that can be found regarding the implementation of the method in order to highlight those steps of the procedure that should be clarified to users. Next. This figure shows the location of the stations of the 8 ocean cruises and 1 coastal time series site where the measurements, carbonate measurements, were obtained during almost a decade between 2009 and 2018. Next. And in this table, you can see all the information relative to each data set used. Mainly regarding the different lead regions solution used and spectrophotometers used. Lead chloride was used in cruises that took place between 2009 and 2012 before the study by Patsabas. And lead perchlorate was used in those cruises performed between 2016 and 2018. The 2 regions were used in 2018 in the RADPROF cruise and in some samplings of the monthly time series. And also we use 4 different spectrophotometers for doing the measurements. Next. This is just a summary of what I said before in the previous slide for consultation. Next. And what we have done is evaluating the 5 approaches of the method through the study of the internal consistency of carbonate ion residuals. We calculated these residuals as the difference between the spectrophotometer determinations obtained with each of the 5 approaches with respect to an expected carbonate concentration calculated from pH and alkalinity. So what we did was to obtain 5 residuals for each absorbance ratio value that we had measured, either if it had been obtained with lead chloride or lead perchlorate. Next. So this figure shows the overall results of this study. These are preliminary results. You can see whisker plots for the carbonate ion residuals obtained that are shown from left to right for each of the 5 approaches of the method. Upper panels show data obtained with lead chloride and lower panels data obtained with lead perchlorate. The x-axis shows the alias of each cruise, and also it shows which spectrophotometer equipment was used for obtaining the absorbance values. The central dot refers to the mean of the residuals, and the red dots are outliers. Sorry. So what we can conclude, the first finding is that the residuals that are obtained with the approaches of Byron, Yao, and Isley et al. Usually yield values close to 0 for cruises that are performing in the Atlantic. And this applies for data that has been measured either with lead chloride or lead perchlorate. While these approaches yield to negative values, which means that they underestimate the concentration of carbonate ion in the Mediterranean cruises, so for high salinity waters, especially when the perchlorate is used. On the other hand, the residuals obtained with the parametrizations by Patsavas and the two approaches proposed by Sharp yield overall positive values. The residuals obtained with the formulations by Patsavas are the largest values, with the only exceptions of the med-wave screws that is surprisingly well centered about 0. And we think that this is due to the perturbation correction itself. Because if you don't take it into account, these residuals decrease by 6 to 15 micromoles and get closer to those that are obtained when using the approaches by Sharp. So the approaches by Sharp usually also yield positive values that are lower, and they get closer and improve and get closer to 0 when the wavelet correction is applied. The outliers suggest that data that is measured with lead chloride shows a larger dispersion, so that this would support the change in region in order to increase the signal-to-noise ratio of the absorbance measurements. But in turn, doing this might cause the need of evaluating and correcting the performance of the spectrophotometer as suggested by Sharp, but the approaches by Sharp. See, for example, the two cruises, last cruises of all the panels that show residuals close to 0 with approaches by Isley et al. And by Bergen Yao, using the two regions. But for example, it still yields positive values when using the approaches by Sharp, even when implementing this offset correction. So overall messages from this figure would be that the residuals show a different response depending on the approach rather than on the region used. And these preliminary results also would suggest that the most modern formulations and the more recent formulations do not always improve the internal consistency, and in turn sometimes add complexity to the analysis because they describe too many considerations to take into account for obtaining a measurement. Next. This slide summarizes all the results commented in the previous slide and describes them more particularly also. Next. So it's for consultation. And this figure shows the residuals, but as a function of the expected carbonate concentrations that are calculated from pH and alkalinity. And then the 5 approaches are shown in different colors. What this figure shows is that the magnitude of the residuals is proportional to the concentrations of carbonate themselves. And this is something that has actually been shown by all the works in the methodology. Yes? Someone talked. So what we would find is that those that yield negative values yield even more negative values as we move towards higher concentrations, and those approaches that yield positive values yield even more positive values moving towards higher concentrations of carbonate. What we can also see is that formulations sometimes are not consistent between them. So you obtain a measurement, but you don't get the same result depending on which approach you use. Next. So this is the same figure. The upper figure shows the same results that in the previous slide, but for those cruises and for the monthly sampling, where we measured sample replicates in order to compare the results obtained with the two regions. What we only wanted to show is that it seems that there is a consistent difference between the observance values that you obtain using each of the two regions in depth. This is shown in depth. So next, this is will be the final slide. So now what we are doing is evaluating by one all the improvements of the methodology, just to guess how to explain the residuals observed. But what we could conclude is that although the 5 approaches can be used for obtaining measurements of carbonate ion, most times they are not consistent between them, and also none of the approaches is a clearly candidate for being implemented globally. So this would bring to a final message that we consider that there is a need to work in a more coordinated way for testing this methodology in more ocean regions and by more groups in order to come up with a validated method by several laboratories for carbonate ion determination. And it would be optimum that it would imply simple best practices that oceanographers could follow if they were interested in measuring this parameter. And that's it.
Thank you so much, Elisa, for that presentation. At this time, I'd like to introduce our final speaker for today, Maribel Garcia Ibanez. Maribel, I've now made you the presenter.
Good. Can you hear me?
Yes, we can hear you.
And can you see my slides?
We could see your slide. They're not full screen yet.
All right. Now we'll try to make them full screen now. Can you see them now?
Yes, they look wonderful. You can take it away.
Okay, thank you. And thank you for the opportunity to present our work during the Ocean Acidification Week. So during this talk, I'm going to show you how discrete measurements of fugacity of carbon dioxide or FCO2 can help us gain new insight into the internal consistency of the seawater CO2 system. Sorry, I'm not changing. Yep. So we have a number of cruises with discrete water column FCO2 measurements, and we wanted to exploit that data set. So what can we use these measurements for? For example, we can use them to estimate anthropogenic CO2, or we can also use them to evaluate the internal consistency of the seawater CO2 system, which is the comparison between measured and calculated values, and that is what we are doing in this work. The advantage of using pH, FCO2, and total dissolved inorganic carbon, or DIC, is that no assumptions about organic alkalinity, or TA, are needed. And in this work, we are using the cruises shown in the map that are available in GLODAP. And all of them have discrete water column measurements of FCO2, DIC, TA, and pH. We split the data set into two groups, the first group being the Woes and Cliver era from the 1990s and 2000s, and the second group being the GOSIP era from the 2010s. But before diving into the internal consistency of the selected cruises, I want to present the thermodynamic sensitivities of the calculated values, and we will first look at the combination of DIC, pH, and FCO2. In the upper row, I'm showing the sensitivity of calculated pH with DIC and FCO2 to errors in the input variables. And you can see that the uncertainties in this calculated pH are mostly dependent on errors and the first dissociation constants of the CO2 system, or pK1. In the lower row, I'm showing the sensitivity of calculated FCO2 with DIC and pH to errors in the input variables. And in this calculated FCO2, you can see that the uncertainties are mostly dependent on errors in pH and in pK1 as well. Only for high pH values, the errors in the second dissociation constant of the CO2 system, or pK2, come into play, generating relatively small biases. But that can be important depending on the goal of the research, since these waters are generally located in the upper part of the water column. Just want to highlight that if we want to get an estimation of FCO2 using DAC and pH as input parameters that has an uncertainty lower than 1%, then the uncertainties in the measured pH and in the pK1 0.005. Continue with the sensitivities of the calculated values. Now we focus on the combination of DAC, TA, and FCO2. And here I'm showing the sensitivities of calculated FCO2 with DAC and TA to errors in the input variables. We see that for low waters, the uncertainties in calculated FCO2 with DAC and TA are mostly dependent on errors in DAC and TA, which compensate one another. And for high pH waters, also the constants of the system come into play. And also want to highlight that in this case, if we want to estimate FCO2 with DAC and TA that has an uncertainty lower than 1%, then the uncertainties in the measurements of DAC and TA should be below 2 micromoles per kilo. However, already the reported uncertainties for pK1 are of about 2% in the calculated FCO2. Therefore, the interplay between all these uncertainties in DAC, TA, and the constant when calculating FCO2 from DAC and TA makes the DAC and TA pair a less suitable option for estimating FCO2 than the pH and DAC pair. And with these sensitivities in mind, we can now begin to analyze the internal consistency of the cruise data. We start with the pH and group 1 data, the Woes and Kleiber era. And in the first upper row, I'm showing the residuals between pH measured and calculated with DAC and FCO2. And in the lower row, the residuals between pH measured and calculated with DAC and TA. The first column is showing the original data set, and the second column is showing where the pH has been correcting following the guidelines of the GOA-ON quality control. Since the quality control in GOA-ON is based on internal consistency between pH, DNC, and TA, applying the suggested correction to pH measurements makes pH consistent with DAC and TA by creating consistencies with the FCO2 measurements. And note that until the new release, GOA-ON didn't contain FCO2 data, and therefore FCO2 was not quality controlled. If we now look at the internal consistency of the FCO2 data for group 1 as well, in the upper row, I'm presenting the relative residuals between FCO2 measured and calculated with DAC and pH. And in the lower row, the relative residuals between FCO2 measured and calculated with TA and DAC. Again, the first column is the original. Second column shows the results when applying the correction to the pH following GOA-ON guidelines. We see that applying this correction to the pH generates an inconsistency with the FCO2, and the distribution of the residuals when applying this correction to the pH is similar for both in the case when calculating FCO2 with pH and DAC, and for when we calculate the FCO2 with TA and DAC. And that was completely the opposite when pH was not corrected with the quality control factors from GOA-ON. In the case on the group 2 data, the GOA-ON era, we can see that the FCO2 is consistent with DAC and TA, and the distribution of the residuals of FCO2 with DAC and TA are different than those of FCO2 measured and calculated with DAC and pH, indicating inconsistencies in pH measurements. We also see that the possible causes of the non-zero residuals in both groups are opposite. So we wonder what is causing this change in the internal consistency. We think that the DIC and TA measurements are an unlikely source of this inconsistency, since the methodologies were consistent between the two periods. In the two periods, CRMs were used to make sure that the measurements were accurate, and also they were quality control with crossovers. So another source of this internal inconsistency could be the pH spectrophotometric methodology. Manual and mainly automated systems. They will also change in the dye, with some recent cruises using purified dye that will increase the precision, but there is not accuracy control. And I want to highlight that this pH spectrophotometric methodology is really simple, but there are some aspects that could be problematic, such as sampling, preservation, calibration and maintenance of the equipment, and the fact that there is no CRM available to pH in seawater. Another candidate that could generate this internal inconsistency in the data set is the FCO2 methodology. There has been different systems used, but they have been compared against each other, and they don't create that observed differences. And again, this methodology has some aspects that could be problematic, such as sampling preservation. The fact that they have to make sure that the calibration gases have to be covering the full range of FCO2 shown in the samples. Finally, another cause of this internal inconsistency could be the constant values used, either the first or the second dissociation constant, but as in other words, we don't see this change in the constant to be the cause of the residual distributions that we see. However, it could point to the fact that we have to reevaluate the K0 for the FCO2 calculations. So I just want to end saying that this points out if we want or we should achieve the internal consistency in the seawater CO2 system. And with that, I want to thank again for this opportunity to present our preliminary work during the Ocean Acidification Week, and thank to all of my collaborators. And I will, Michael, thank you.
Thank you so much, Maribel. At this time, I would like to thank all of our speakers today for their wonderful presentations. And I'll ask all of our presenters, if possible, to turn on their cameras and to join us for a question and answer session. At this point, everyone should be able to see my screen. And before we get into the question and answer session, I want to remind the audience members that they can type their questions into the questions box, or they could pose their questions on Twitter using the hashtag OAWeek2020. You could @GOA-ON. And if you have more specific questions for the Northeast Atlantic Hub, you could use their hashtag or @them at GOA-NE. I would also like to notify the audience that we have 3 more sessions of Ocean Acidification Week. The second Northeast Atlantic Hub session will take place in just a little bit, right after this session ends. And then afterwards, we will have a session called Friends of GOA-ON. We'll be hearing from other organizations that conduct work in the ocean acidification field. And then finally today, we'll have a capstone presentation, which will feature the co-chairs of GOA-ON, as well as a co-chair of the high CO2 meeting that I mentioned at the beginning of the webinar. So without any further ado, we will move into the question and answer session. And we'll begin asking our panelists some questions. One last thing to mention, we have a lot of questions coming in, which is wonderful. If we don't get to all of these questions within the next 15 minutes, we will continue the conversation on the Ocean Acidification Information Exchange. This is a website, a social media platform really that's tailored specifically to ocean acidification researchers, decision makers, and stakeholders. If you're interested in ocean acidification or you work in that field, I highly recommend that you become a member of that site, and you could do so by logging on to oainfoexchange.org. All right, so let's get started with some of these questions. The first question comes from Jean-Pierre Gattuso, and it's for Filippa, and he asks, thank you for the great presentation. Have you identified the cause of the increased total alkalinity? Filippa, we can't hear you. Try unmuting yourself now.
Oh, now it works.
There it goes.
Sorry, I didn't hear. The increased pole alkalinity? That was the question?
Yes.
No, we've been discussing it between the quarter. So one part of this increased alkalinity is probably related to the increase in salinity that we see. But then we see an exceptionally large increase in the Barents Sea opening, and we don't know what it is, and it would be interesting to dig further into that.
Thank you very much. The next question is for Rachel, and it comes from Gellert Mueller. They ask, do you see any effect of primary production or remineralization on your pH profiles?
Yes, for sure. I mean, you see that in the difference in the summer and winter in the surface ocean, because if you've got primary productivity going on, that's drawing down the CO2. So that means your pH is actually rising because you're taking CO2 out of the water. And we also see it then in the mid-water oxygen minimum when you're remineralizing all that material that's fallen down from the primary production. So that is going to then produce CO2, and that's going to then pull down your pH. So there is one of the reasons we do most of our transects in winter is so that we can kind of take out the primary productivity effect and see what's going on just with the water masses. But then it's also really interesting to compare winter and summer just to see how much difference the primary productivity makes from year to year.
Thanks, Rachel. And then there's a follow-up question from Libby Jewett, and she asks, do you have any sense of how much Aragonite saturation horizon has shallowed since pre-industrial revolution?
Yes, we do have a pretty good idea that our pH is changing about 0.01 per decade at the minute. I need to check on this, but I think it's about 500 meters in that area. So in the Rockall Trough. Since then, we think it would have been certainly down at 2,500 meters or more, and it's now about 2,000 meters. So I think I'm correct in saying that. I'll have to go back and see, but I think it's about that. Philippa might have actually maybe some information about that as well. Mm-hmm.
All right, thank you. Perhaps after the session, we could continue talking about this specific item on the Ocean Acidification Information Exchange. Our next question comes from Andrew Dixon, and it is for Elisa. Elisa, are you able to unmute yourself? You should try giving it a shot now.
Yes.
Okay, great. So Andrew Dixon asks, the carbonate uncertainties, which were listed in an early table as 2%, does the scatter on your data support this?
Yes, we find uncertainties of this, but for some in some ranges of the carbonate concentration, but the residuals become even larger at some point, and we don't really understand why. So it would work for a range of the carbonate concentrations, but not for the whole range.
Thank you. This next question is for Maribel, and it actually also comes from Andrew Dixon. He writes, you describe some problems that may cause inconsistencies during observations. However, every cruise may have some internal problems. How would you plan an experiment to better resolve the causes of some of these observed problems?
Thank you for the question. So I was in fact a paper from McElligott et al., and they were already dealing with this inconsistency with the SU2, PHDAC, and TA. And they already proposed a really good experiment that I think OAN did. So instead of only doing lab experiments with really quality control labs and everything, so do the experiment on sea using boats and like the conditions where the measurements are taken, and do exactly the same as they do in the lab. Prove that during not that ideal conditions, there is internal consistency of the system. So I hope that answers the question.
Thanks, I think it does. The next question is actually for all of the panelists, and I hope that we could go around and each of you can provide some insight. How can early career researchers in your region become involved with OA research?
Well, I guess the first thing is to let us know. Email any of us on the panel, I suspect, but certainly you can certainly email me if you're interested in OA research and come and talk to me. Depends on what stage you're at. But there's certainly plenty of work to be done. The issue, as always with science, is how much funding we have to pay people. But we're certainly, if people are interested in getting involved in OA research, there's all sorts of stuff right from coastal all the way out to the maximum ocean depths.
I just say, as co-chair of the hub, if you want to find out more specifically for our region, please do get in touch with myself or Steve Widdicombe. Follow us on Twitter. We will try and post any jobs or early career events that are coming up. Social media is probably one of the most active places that these sort of things come up. So we're very willing to share. And also, like Mike said, the Ocean Acidification Information Exchange is a wonderful place to find out about all opportunities around the world for ocean acidification. So do just get in touch and get in contact with our networks.
Do any of the other presenters, panelists have other things to add? Vass, it looks like you're muted. Let me see if I can help you out with that. You should be good.
I am sorry about that. I always think you need a little bit of luck early on in your career. You need to be in the right place at the right time. But also you make your own luck. You put yourself in that place at that time. And like Rachel said, don't be shy. Come and talk to us, and find there are always some opportunities, as Helen says. So what we're looking for is enthusiasm.
Well, hopefully the right place and the right time is Ocean Acidification Week, and right now. And I think we have about 5 minutes left. I'm going to ask one other question of all of the panelists. And it is, are people in your region aware that ocean acidification is happening? And if not, what can be done to raise awareness?
Well, I guess I can start. Yes and no is the answer to the are they aware? Shellfish are...
So I've been doing research, yeah.
Seems to be a little bit of a lag. So why don't we start with Rachel, and then I think, was that Maribel who spoke next? So we'll go Rachel, Maribel, and then we'll go from there.
Okay, so I said yes and no to awareness. So anybody who works in water is aware of it, whether freshwater or saltwater, because acidification also is happening in our freshwaters as well. The shellfish growers are all aware that this is kind of coming down the tracks to potentially upset their industry. The general public, probably not. But we are now, certainly in Ireland, we're starting now to run sessions in schools to kind of, get kids understanding how acid dissolves shells and so on, and sort of get it into that end of it. Sometimes ocean acidification is a bit too much chemistry for people, so we have to kind of be careful that we don't overdo it and say, oh, all the shells are going to dissolve, because that's kind of a serious exaggeration. But also not to be too heavy on the specifics of the chemistry, because that people are a little bit like maths, they're very afraid of it, unfortunately.
Maribel, did you have anything to add?
I agree with Rachel. I was going to say something similar. So most of the scientific community are aware of it, but the general public is more towards the CO2 problem with climate warming, but not that much in ocean acidification. And as Rachel said, we don't need to be that alarmistic to say everything is going to die in the ocean because of that, but we should be aware, make the general public aware that this is happening. And the strategy one, and maybe just try to approach, I don't know, with social media or other forms, the general public, and not that much from the chemistry part, because that's really difficult, but more towards what is happening in general terms, and just make people aware of it. That's kind of the other problem of the CO2, that not a lot of people know about it.
Do any of the other panelists have anything to add?
I'll just add, again, from the hub perspective, one of our aims is really to try and improve our communication for ocean acidification to scientists, but also to the wider general public and also policymakers. And we've been working hard to get the message out to policymakers at the United Nations Framework for Climate Change Conventions, and also some of the virtual events that have taken place this year. You can find some of the talks of those online. If you go to our hub website, you should be able to get access to those if you want to see the videos. We also work quite a lot at Plymouth with an educational outreach company called Encounter Edu, EDU, who work to produce ocean acidification and other material for free resources for schools. So we'd like to continue our work with that and also promote ocean acidification across our hub. So translating from the English resources that we currently have available or plan to make in the future into the regional hub languages, so French, German, etc., Spanish, to really be able to provide that opportunity to the general public. So watch this space. Hopefully we should be getting some more resources available over the next year or so, funding allowance, but that's our intention.
So I saw Vass had his hand up. Vass, could you respond, but make it quick, maybe in 30 seconds, and then we'll wrap up the webinar.
Yes, I was just going to add that I think we have a language problem when we're trying to reach the general public. So we talk about ocean acidification, and in the same breath we talk about uncertainty. We understand what we mean about uncertainty of measurements, predictions. But the general public, when they hear the word uncertainty, they think, well, it might not happen at all, which is wrong. So we need to think about the language that we use very much.
Seems to be like a language jargon problem, as well as translating to different languages and maybe not always relying on English. This has been a really great discussion, and I'm excited to continue it on the Ocean Acidification Information Exchange. There was a lot of technical questions that came in, and a few other kind of broader panel-wide questions that I will copy to the OA Info Exchange sometime after the webinar. I want to remind our audience that we have part 2 of the Northeast Atlantic Hub OA Week sessions happening in just a little bit, and we hope to see you there very soon. One last time, I'd like to thank our panelists for today and giving those wonderful presentations. Thank you so much for joining us for the 7th session of Ocean Acidification Week, and we'll see you all back here very soon. Bye.
Okay, thanks a lot. Okay. Right.